Hello and welcome to SudoKanard. Here's a puzzle that was published by Indian author Akash Doulani on his blog, and that's not the typical Sudoku puzzle you find on his blog. Generally, Akash sticks to just one constraint, just one variant, but there he did some hybrid with killer cages, with Kropki pairs, with 5 pairs, with 10 pairs, and that's it. And pairs means that here the sum of those two digits should be 5, but the lack of symbols anywhere else does not mean they couldn't add up to 5. That's still a possibility. Same with those which must be consecutive, but those might be consecutive. Here one must be double the other, and in cages, well, one of the digits has to be double the other. So where do you start? Well, 15 and 13 are big digits. 15 could be 7, 8, or 6, 9. And in both cases, we can deduce what is in the 13 cell, in the 13 cage. And if I recall correctly, oh yes, what I didn't mention is that it took me quite some time to solve the puzzle because I needed to find something. And I put the link in the description. You should try to solve it by yourself before watching my video. So I tried both possibilities and pondered the consequences. If I put 7 and 8 here, then the only option for 13 is 4 and 9. And in this case, the only option remaining here is 5 and 7. And what happens here? Then this doesn't use 7 or 8, so this is 3 or 9. And I can deduce that this is 1 and 4. And at this point, this should be 3 and 6, I think. But then, generally, when I do something like this, my intent is to find some contradictions, something that tells me that, well, this option is in the end not possible, but this looks quite possible. So let's try the other one. But let's recall something. Let's recall that in this case, we get 1 and 4 here. So the second option is to try 6 and 9 here. And in this case, this 13 cage can only be 5 and 8. And this here can only be 3 and 9. And knowing this, in the other option there was 3 and 9 here, now there is 3 and 9 here, so that this has to be 1 and 4. So whatever I put here, this has to be 1 and 4. But now that this is 1 and 4, what are those digits? They can't be 1 and 2, they can't be 2 and 4, they can't be 4 and 8, they can only be 3 and 6, so that this can't include a 6, and it must be 7 and 8. And now this has to be 4 and 9, not 8. This has to be 5 and 7, and this now has to be 3 and 9, and that's a very nice beginning. This is consecutive with one of those digits, can't be 4, can't be 7, so it has to be 2 or 5. And actually on this row we still need 1, 2, and 5, and this can't be a 5. On this row, we still need 2, 6, and 8. So this will have to be 2 or 8. 2, 6, or 8 here. And what else? We know that here we have somewhere a 7 or a 9, or 7 and a 9. And they can't both be here because they are not consecutive, so one of them is here. And the other one is here, together with a consecutive digit. But 7 won't be with a 6. So 7 will be with an 8, and 9 will be with 8. That's the only consecutive digit. So this includes an 8 together with a 7 or a 9. And now this is 2, this is 5. So this is 6, this is 3. There's no 2 here, there's no 2 here, there's no 5 here. And that's a neat start. That's a very nice logic. And this is where matters get much more complicated. Because now, what other logic can be deduced from the remaining clues? Well, that's really not easy to see. We can see that because of this triple, this can't be 7, 8, or 9. So it will only be 6 with a 4. Or here, a small digit, like 1, 2, 3, with 7, 8, or 9. But that's still 4 options. Actually, not that many. Yes, that many. We could think of what is here. Oh, 7, 8. Sorry, that's a 6, and that's an 8. All right. So here we know that there's an odd and an even digit. We know that this can't be 1 and 2 because of this, so it can't include a 2. It could be 4 and 5, and actually it could only be here. Oh, it could only be that. We need 1, 2, 4, and 5, so this has to be 4 and 5. This is 1 or 2. This is consecutive, so this is 1 or 2, 1, 2 or 3, and this is 7, 8, or 9. But this is not a huge breakthrough. We know that here we have 1, 4, or 2, 3, but that doesn't seem to be a way to resolve that. And now I think is the right time to show you something quite tricky to spot, but really beautiful. Let's use colors. And let's note that, oops, sorry about that. I find another color. I said, let's say this color. Well, let's say this color. Let's have a look at those 4 2x2 blocks. If you're familiar with Fistomethyl ring, the principle of the Fistomethyl ring, well, something similar is happening here. Let's choose another color. Let's say red. And then, well, what is happening? What I'm claiming is that the digits that I've just highlighted are the same as the digits that I am highlighting now. And why should it be so? You may be wondering. Well, let's use yet another color. Let's say something like yellow. And let's highlight all of those cells. So now what is happening? What is happening is that if you take all those 4 columns, they contain 4 times every digit from 1 to 9. And this is yellow and green. So yellow plus green, the union of the yellow region and the green region is 4 times all digits from 1 to 9. And now if you take all digits that are yellow or red, then you have those 2 rows, and those 2 blocks, 2 rows and 2 blocks, that's 4 times all digits from 1 to 9. So we have 2 sets that are four times all digits from 1 to 9, and if you remove the common part, that is, if you remove the yellow, then you should have the same digits on the rest of them. And why is it useful, you may ask? So now we know that all the green part here is the same as the red part here. And why is it useful? I was asking. Let's remove all of this. Well, this is useful is that all the cages here have a minimum of 11, so they cannot contain a 1. So we know that all green digits are different from 1, and therefore all the red digits must be different from 1 as well. And the consequence of that is that this must be a 2-3 pair. Sorry about this, a 2-3 pair, it can't include a 1. So we get a 1 here and a 2 there. So this is not 2, this is not 8. We get a 7-9 pair here, which is nice. And then we know that, well, this 2 puts a 2 here. Here that must be a 1-3-6 triple. But this can't be a 1 because it's a digit in red. And this now has to be 704. Where else can we look? So we know that there's no 1 in here. What else is a place of interest? That in itself was the reason I decided to solve this puzzle on video. I just don't remember what remains to do now. I think there's an interaction between those digits. Let's imagine this is 3. Then this has to be 7 to have a sum of 10. Then this has to be 4. And then there's no option for this 5 sum. So putting 3 here led to a contradiction. So this is 1, this is 9, this is 7. There's no 7 here. And now this is a 2-3 pair. So that's some progress again. What do we have here? Oh, let's have those ones. Put a 1 down there. But 1 can't be in an 11 cage of 2 digits, so that is a 1. And in this region now 1 can only be here. In this region we know that 1 is not in the red region, 1 is not here by Sudoku, 1 is not in an 11 cage, so 1 is here. But 1 here would put a 9 here because of this 10 symbol, so 1 is here with a 9. So that's not 1, this is 1. Is there anything about the last one in the grid? Well, there has to be a 1 somewhere here, and we don't know anything about this. There has to be a 1 somewhere here, and we don't know anything about this either. What else is there to see? That's a valid question. Something I'm seeing here is that because there's a 9 here, this 11 can't contain a 2. And this is not a 2. There's no 2 here because of this. So there's a 2 here and an 8 there. And this can only be a 3 because of this one. And this 2 now makes this a 3 and this a 2. So now this 12 can't be 3 and 9, and we know that it can't be 5 and 7 because of this. So this must be a 4-8 pair. And this is now a 9, this is a 4. The missing digits in the column are 5, 7, and 6. And if I try to put a 7 here, then this would have to be a 5-6 pair, and this would also be 5 or 6, and that wouldn't work. So that's a 5, that's a 7, there's no 5 here. 7 here would put a 4 there, which doesn't work, so this is 6, this is 7, this is 5. The 7 makes this a 4, that's a 6, that's a 3, and 3 goes there, and that's an 8. We need another 11, it can only be 2 and 9, and this is 6. Consecutive digit here is 5 or 7, and here we have 1, 4, 5 or 7. That is still some good progress. Here we still need 4, 5, 6, and 7. This is 4 or 6. This is consecutive, so this is 5 or 7. And we have the other 2 digits here. What can this be? It can't be 3 and 8, can't be 5 and 6. There are still 2 options, 4, 7, and 2, 9. What about the 2? Actually, in this region, 2 can't be here or there by Sudoku. 2 can only be here. So that's a 2 and a 9. This 9 makes this a 3, this a 9. Here we know that there's a 1 somewhere. Oh, and this 5 and 6, they must be here. So that's a 5, that's a 6. So this is 1, 4, 7. 7 is not here. And this is now 8. Those must be 5 and 6. So this is 5, this is 6. 4 and 5. 4 and 7 here. 7 and 9 here. So this can now only be 3 and 8. So up there we get the 7 and the 8. That's the 4 and the 7. This can only be 5 and 6. And this is now a 4. The options here are 5, 7, 8, and 9. So this can only be 8. This is 7 or 9. 5, 7 or 9 here. This column still needs 1, 4, and 3. 4, well, 3 here would put a 6 here, which would clash with this 3, so this is not 3, and 3 is here, with a 7, so that's 9, that's 5, that's 7. This 7 puts a 9 here, and 7 there, this 9 puts a 2 here and a 9. This 3 puts an 8 here and a 3. This 8 puts a 4 here and an 8. This is now 1 or 6. We still need a 2 somewhere. And 2 here would put a 1 there and a 4 there, and it would break. So 2 is here. 1 and 4 are both valid, but the only consecutive digit is 1. So that's 6, that's 4. 5 and 1. That's a 1, that's a 4, that's a 7. That's 3, that's 2, that's 8, that's 9. And that's 1, and that's 4. Oh, and here we get a 6 and a 5. And it completes the solve of this puzzle, which was really on the difficult side of things when you consider what Akash publishes on his blog generally. That was beautifully constructed as always, but I'm wondering if there's another way of solving it, I mean without spotting this modified Fisomyphal ring, which is what is sometimes called set, SET, set equivalence theory, meaning that this green set is equivalent to the red set, and you can check that the digits are exactly the same in both regions, in both outlined regions, both shaded regions. Right, so thanks for watching this video and see you soon on SudoKanard.